Hello and welcome back to Machine Learning. I'm Jovita Christie, and in this video, we are going to talk about multiple random variables. We've already seen what random variables are, but in most practical purposes, there are two or more random variables involved on the same sample space. So that's why we have to talk about multiple random variables. We are just going to quickly take a look at different formulae associated with these. And we are also going to take a look at the central limit theorem. So first we will see bivariate random variables where there are two random variables in the same sample space. Okay, so two random variables x and y in the same sample space of S of a random experiment. And here the pair x comma y will be a bivariate random variable or a two-dimensional random vector where each of x and y are associated with a real number for every element of S. Okay, and the range space of a bivariate random variable can be denoted by Rxy, and that means all the possible values, and xy can be considered as a function that to each point zeta in S assigns a point small x comma y in that plane. And this is how you can calculate the range of xy by using all points x comma y such that zeta belongs to S, which is your sample space, and x zeta is equal to small x and y zeta is equal to small y. Now x comma y is called a discrete bivariate random variable if the random variables x and y both by themselves are discrete. So if x and y both are discrete, then this bivariate random variable will also be discrete. And similarly, x and y is called a continuous bivariate random variable if the random variables x and y are both continuous. Okay, now what happens if both are not continuous, or if one is discrete and one is continuous? Then it will be called a mixed bivariate random variable if one is continuous and one is discrete. And here are some formulas for this. So the joint distribution function for these x and y can be calculated like this. P of x less than equal to x and y less than equal to y. For the event x less than equal to small x, y less than equal to small y. And we can define capital A as the set of all zeta belongs to capital S sample space such that x zeta is less than equal to x, and you can define the same thing as B. So if there are two events like this, A and B, then you can calculate the probability of A in this manner, and you can calculate probability of B by using the Fy function, which is the cumulative distribution function. Okay, and because there are two variables, we are using the joint distribution function, which is simply the probability of A intersection B. And if you have certain values of x and y, if A and B are independent in sample space S, then you can calculate f x and y as P A intersection B, which is equal to P of P probability of A into probability of B, and you replace that with these two functions that you created right here, and you know how to calculate the function using this formula. Now let's take a look at joint probability mass functions. So that was probability distribution functions. Now let's take a look at mass functions. So if you have discrete bivariate random variables x and y, and they are taking values xi and xj for some integers I and j, then you can define the PMF in this manner. So it's the same formula as before, except here we are not using the less than equal to sign. Instead, we are using just equal to xi and equal to yj. And if you want to calculate the joint PDF of a discrete bivariate random variable x and y, it can be calculated in this way. So there are two sigma functions because there are two variables, and this is the probability of xi comma yj. So this is how you can calculate it. And along with this, there is also conditional distributions. So what is conditional distribution? While you're working with a discrete bivariate random variable, it is important to deduce the conditional probability function as x and y are related in the finite space. Okay. So based on the joint PMF of x and y, the conditional PMF of y when x is equal to xi can be defined in this manner. Okay. So P of y given x is um, yj given xi, and you can calculate it like this. When px of xi is greater than 0, and if py of yj is greater than 0, then you can also calculate the reverse of this. So this is another formula for that. So you can apply even conditional probability to bivariate random variables by just modifying the formula. And you can also calculate the covariance and correlation. The covariance between these two variables would measure the degree to which x and y are linearly related. Okay, means how x varies with y. Is it inversely proportional, directly proportional? And to calculate that, you just have to calculate E of xy, which means the mean of x and y together, and subtract that from the mean of x multiplied by the mean of y. So if the variance is the measure of how a random variable varies with itself, then covariance is the measure of how two random variables vary with each other. Okay, so variance is for one variable, covariance is used for two different variables. Now let's solve a problem related to multiple random variables. So let's say that I roll two dice and I observe two numbers x and y, where x is associated with the number shown on the first dice and y is associated with the number shown on the second dice. First, the question is to find out the range of x and the range of y. And then we are supposed to find out the PMFs of x and y. So first, let's find the range of x. So when we are trying to find the range of x, it just means what are the possible values that x can take. And we know that a dice has 6 sides and 6 numbers from 1 to 6. So that means my Rx would be all the numbers in this manner from 1 to 6. And my Ry is also going to be all these numbers. And next I have to find the PMF, the probability mass function of x and the probability mass function of y. Both of them are discrete random variables because they take one of these values from 1 to 6, and so they have some specific value, which is why it is discrete. And to find the PMF of x, we are simply going to write Px of k is equal to, now probability of getting any of these values from 1 to 6 is going to be 1 by 6 because there are 6 possibilities. So it is going to be 1 by 6 whenever k is from 1 to 6. And it's going to be 0 otherwise. Okay, and the same is true for y. So when I'm writing Py of k, it is going to be the same thing, 1 by 6, where k is this value from 1 to 6 and 0 otherwise. So that's very simple to do. Finding the range and the probability mass functions of x and y. So that's very simple. Let's take a look at another question. This time, I want to find the probability of x equals to 2 and y equals to 6 at the same time. So if you know this actually is known as joint probability. This is a concept we studied when we studied conditional probability, and we studied the Bayesian concept. If you need a quick refreshing of these concepts, if you want to revise them, I have provided a link in the description box, and you can access those videos. Now, what we need to find is P of x equal to 2 and y equal to 6. And for this case, this is nothing but probability of x equal to 2 into probability of y equal to 6. Now remember, we are doing this because these two variables are independent. They are not dependent on each other, because getting some value on the first dice, for example, 2, does not affect getting some value on the second dice. So these two are completely independent. And so when I find the joint probability, I can just find it by multiplying the two, and probability of x equal to 2 is 1 by 6. We know that, we just created the PMF. And y equal to 6 is also 1 by 6. And if you calculate, if you multiply, you'll get 1 by 36. So that is how you can solve this kind of a problem. Let's take a look at another one. Now I want to find the probability of x greater than 3 given y equal to 2. So this is a question of something called the conditional probability. Now what we need to find is x greater than 3 given y equal to 2. But we know that x and y are actually independent. So because I'm getting 2 on the second dice, it has no effect on what I get on my first dice. So probability of x is not affected by the probability of y. And therefore, I can just write that this thing is actually equal to just finding the probability of x greater than 3. And probability of x greater than 3 is simply probability of getting x equal to 1 plus probability of getting x equal to 2. Sorry, it's not going to be x equal to 1 and 2, it's going to be the opposite. So I'll just remove this part. Okay. So probability of x equal to 4 and x equal to 5 and x equal to 6. That is what I have to find out. All are greater than 3. We don't have any other numbers. So all of these are actually 1 by 6 because we know everything has equal probability. And so that is going to give me 3 by 6, which is going to be 1 by 2, which if you want to go further would be 0.5. So that is how you can calculate this value. Now let's take a look at another value. Let's find out another variable z. And what we have for z is actually, we want to define z as z equal to x plus y. And we want to find the range of z as well as the PMF of z. So first of all, let's calculate the range of z. Remember that z is equal to x plus y. So to calculate the range of z, we will get all the possible values that you can get by adding x and y, and you have to consider all values of x and y. So if you think very carefully, then you are going to get the value. You won't be getting the value 1 because we don't have zeros in either x or 1. So the minimum value you'll get is 2. And the maximum value you will get is 12 because x can be 6 and y can be 6. So it's actually all the values from 2 to 12. Okay, so the range is equal to this. You can get all these values by adding x and y. And to calculate the PMF, you have to find the probability of getting all of these values. Now, how to do that? So first, let's calculate the probability of z being 2. Now, when can z actually be 2? So z can be 2 when you have x equal to 1 and y equal to 1, which means you have to calculate the combined probabilities of x1 and y1. And this is equal to, when x is 1 and y is 1, so probability of x equal to 1 is 1 by 6. And probability of y equal to 1 is also 1 by 6, which means probability of z equal to 2 is going to be 1 by 36. So that's how you can get probability of z equal to 2. Now let's calculate another probability. Let's calculate this time probability of z equal to 3. So when can you get the probability of z equal to 3? When you have x equal to 1 and y equal to 2, or you have x equal to 2 and y equal to 1. These are the only two possibilities, which means you're going to be doing 1 by 6 into 1 by 6 plus 1 by 6 into 1 by 6, because all the probabilities are this, which means, in other words, you are doing 1 by 36 plus 1 by 36, and that's going to give you 2 by 36, which would finally result in 1 by 18. So this is for probability for z equal to 3. And similarly, you need to calculate the probabilities for all the values from z equal to 2 to z equal to 12, and you need to find the final BMF. Now let's calculate the probability of z being equal to 4. So for z equal to 4, we can write down P of z equal to 4. And what can happen here is you can get probability of z equal to 4 by calculating probability of x equal to 1 and y equal to 3, plus the probability of x being 2 and y being 2, and then add to it probability of x being 3 and y being 1. So there are three things, which means in total you will be having 3 times 1 by 36, which is going to give you 1 by 12 again. So this is 1 by 12 for probability of z equal to 4. And similarly, now you get the gist of it, of how to calculate this. So you can have probability of z equal to 5. And this, if you want to calculate this, you just have to find out how many possibilities are there. So for z equal to 5, you can have values of x as 1 and 4, x and y as 1 and 4. You can have 2 and 4. Sorry, you can have 1 and 5, 2 and 4. You can have 3 and, yeah, that was correct. So 1 and 4, 2 and 3. You can have 3 and 2. And then you can have 4 and 2. So you have 4 possibilities, which means you're going to get 4 by 36. And 4 by 36, if you evaluate it, you get 1 by 9. So that is for z equal to 5. For z equal to 6, you will have more possibilities. So you will have this time 1 and 5. You can have 1, 2 and 4. You can have 3 and 3. You can also have 4 and 2. You can have 5 and 1. So that is this many possibilities, which is actually 5. So it will be 5 by 36. And 5 by 36, you cannot evaluate it any further. So that's the answer. For z equal to 7, if we calculate, for z equal to 7, there will be 6 possibilities. I'm not listing them out. You can find out for yourself. So that will be 6 by 36, which if you evaluate will be 1 by 6, because 6 into 6 is 36. Next one is z equal to 8. So for z equal to 8, you will be having 5 different possibilities once again. And you'll notice that it's now going to repeat. So z equal to 6 is the same as z equal to 8, which will be 5 by 36. And similarly, if you proceed, and if we try to find out now probability of z equal to 9, it's just going to be the same as probability of z equal to 5, which was 4 by 36. And if you evaluate it, you get 1 by 9. Probability of z equal to 10 will be 3 by 36, which will come to 1 by 12. Probability of z equal to 11 will be 2 by 36, which will come down to 1 by 18. And then probability of z equal to 12 will be finally 1 by 36, just the same as probability of z equal to 2. So these are the possibilities. And you can create one nice, neat looking function that looks like this. You can see here you have probability of z, and I have listed out all the possibilities, but I have also taken care of the fact that sometimes we have these very probabilities that are repeating. So 1 by 36 is same for k equal to 2 and 12. It's the same as 3 and 11 for 1 by 18. 4 and 10 both give you 1 by 12. 5 and 9 both give you 1 by 9. And 6 and 8 give you 5 by 36. And 7 gives you 1 by 6. So this is a probability mass function of z. Let's see what else you can calculate. So let's find out the probability of x equal to 4 and z equal to 8. So we want to find the x equal to 4 and z equal to 8. Now for this kind of a question, first of all, also you can verify your previous answers of the PMF by adding all the probabilities, and if you get a 1, then that means your answers are correct. Now, what we want to find is x equal to 4 given z equal to 8. This time, we cannot say that x and z are not dependent on each other. X depends on z very much. And to calculate that, we need to find actually the probability of x equal to 4 and z equal to 8. So the joint probability of these two, divide that by the probability of z equal to 8. And what that essentially means is, suppose your x value, z is actually nothing but x plus y. Now, if you're given that y is equal to 4 as it's given in the question, then what can be the value of y when z is 8 and x is 4? It can be 4. So what you actually want to calculate is x equal to 4 and y equal to 4, and divide by probability of z equal to 8, which is quite easy to calculate. We know that x equal to 4 is 1 by 6, and y equal to 4 is also 1 by 6. And for z equal to 8, we can just go back and check out. So for z equal to 8, we have 5 by 36. So we can just put those values here, 5 by 36. So this will be divided by 5 by 36. And that whole thing will be equal to 1 by 5 when it is evaluated. So this is the probability of x equal to 4 given z equal to 8. Now let's take a look at another very important concept in probability and statistics, which is the central limit theorem. And it just says that with a large sample size, the sample means are normally distributed. Okay, so if you go on increasing the size of your sample that you have taken from a population, then the means of those samples, that means the averages of those samples, will become normally distributed gradually as you go on increasing your sample size. Okay, so according to the central limit theorem, the mean of a sample of data will be closer to the mean of the overall population in question. Okay, as the sample size increases, notwithstanding the actual distribution of the data. So as you go on increasing the sample size, your average of the sample will start becoming equal to the average of the population, which is quite obvious, because if you have taken initially just 10 people out of 100, and you are taking, if you've taken 10 values out of 100 and you're taking the mean and compare that mean with the mean of the 100 values, then obviously it's going to be different. But the more number of values you increase, for example, taking 20 values, 30 values out of 100, 40 values, you will notice that the average keeps on getting closer and closer to the average of those 100 values. Okay, so data is more accurate whether the distribution is normal or not. Let's take a look at some formulas associated with the central limit theorem. So the central limit theorem states that if you have a sequence of x variables which are independent, identically distributed random variables, which are also known as IIDs, okay, and so that means they are independent variables, x1 up to xn, they are all independent, but they are identically distributed, which means the probability distributions of all these x variables is going to be same. It can be anything, but it is going to be same. And each of them, they have some value of mean and variance. And you can specify that bar xn is equal to 1 by n into the sum of all the xi values. And so you can specify that Zn is equal to xn minus mu, which is the mean, divided by sigma, which is your standard deviation, root n. And central limit theorem says that if n tends to infinitive, which means if you have a really large set with you of x values, but it is a finite set, then the value of Zn also tends to the standard normal form. And for a standard normal distribution, we know that the mean is 0 and the variance is 1. So that's what we have specified here. And that's what the central limit theorem tells us. So to conclude, according to the central limit theorem, irrespective of the distribution of the individual xi's, the distribution of the sum, which is Sn equal to x1 up to all the values up to xn, is approximately normal for a large value of n. And it's a very important result, as whenever you need to deal with a random variable, which is the sum of a large number of random variables, then this central limit theorem is going to help you out because it says that this sum is going to be normally distributed. So I hope you understood all this, and I'll be back with the next video. So see you there, and thank you for watching.